Hi guys, in the last lecture what we covered is we saw how to determine the circuit parameters of the equivalent circuit of a transformer. So for that we studied two type of tests. One was the open circuit test. In open circuit test we determined core losses and we determine the shunt parameters of the transformer equivalent circuit R0 and X0. Open circuit test was conducted at rated voltage. So it was being conducted on the low voltage side because the rated voltage of the low voltage side is less. So it is easier to apply the rated voltage on the low voltage side. Then we studied about the short circuit test. In short circuit test, what we studied is it was being conducted at the rated current. Since high voltage side will have less rated current, so it was being conducted on the high voltage side, with low voltage side being short circuited. It was used to determine full load copper loss, and we determined the series parameters of the equivalent circuit, which is R01 and X01. So this was what we covered in the last lecture. In this lecture we will try to understand what kind of losses occur in a transformer and what are the significance of different losses. So basically there are four type of losses that we consider in a transformer. First is called as copper loss. Copper loss is actually the loss that occurs in the winding of the transformer, and since the winding is made of copper, it is termed as copper loss. Next is called as iron loss or core loss. Due to alternating flux being set up in the core of the transformer, there are some of the losses that are associated with the core, like hysteresis loss and eddy current loss. Those two losses are called as core loss or the iron loss in a transformer. The third category is stray load loss, and the last one is dielectric loss. In this lecture we will cover each of these losses in detail. What are these losses and where do they occur? So first let us start up with the copper loss. So basically copper loss is concerned with the winding resistance. Okay, this is the loss in winding resistance. Okay, so copper loss can be written as I1 square R1 plus I2 square R2. And when we studied winding resistance, as I told you, this is equal to I1 square into R01. R01 is the equivalent resistance referred to the primary winding. It is equal to I2 square into R02. So R02 is the equivalent resistance referred to the secondary winding. So we see that the copper loss is proportional to I square. So when we talk about copper loss at full load, we will call it as I full load square into R01 full load on the primary side, or I full load square 2 into R02. I full load 2 means full load current on the secondary side. Now usually the transformer may not be working at the full load. Usually the distribution transformer, the transformers that are located at near our homes, they do not work on full load. Why? Because the load on the transformer varies. In the daytime we may not switch on the tube lights, in the night time we may switch on the tube lights. So the load is variable, hence they do not operate at full load but at a variable load. So how is the loading defined? Loading is defined as I is equal to X times I full load. Okay. If someone is giving, let us say, X% of full load, it implies I is equal to X by 100 into I full load. Means the loading is defined in terms of current. 10% of full load means the current that is flowing is the 10% of the full load current. That is what is meant by loading. Now I know copper loss is proportional to current square. So what I will say is copper loss is equal to X square times PCU FL, or in terms of percentage you can say X square by 100 square. So copper loss is proportional to loading square. Okay, loading just means what percentage of the full load current is flowing in the transformer. So copper loss will contain a factor of X square. Sometimes we will be studying per unit system in the case of power systems, but now if we consider in per unit system, sometimes full load copper loss will be given in terms of percentage. Percentage full load copper loss is equal to percentage resistance drop. Okay, this percentage system or the per unit system will be covered in case of power systems, but you must be well aware of that per unit system so as to consider the losses and the power in terms of per unit or the percentage. So percentage full load copper loss is same as percentage resistance drop. Is it fine? So this is what is about the copper losses. The one most biggest confusion in terms of students is they do not differentiate between the copper loss and the copper loss at full load. So remember, copper loss is nothing but it is the loss that occurs in the winding of the transformer at any value of current. No need to specify the current. Whatever is the value of current, the loss in the winding will be called as copper loss. But copper loss at full load means the loss or the copper loss that occurs when the full load current is flowing in the winding or the rated current is flowing in the winding of the transformer. So do remember to differentiate between these two. The relation between these two is this. X is in terms of percentage. If X is in terms of fraction, we will write PCU is equal to X square PCU FL. If X is given in terms of ratio or the fraction. Okay. So remember this difference between full load copper loss and copper loss at any other value of current. The next type of loss is called as iron loss. Usually the core of the transformer we saw is made of silicon steel, and steel is a form of iron only. Steel is made from iron. So we can say that the core of the transformer is made of iron. Hence, the losses that occur in the core are called as iron losses. So, these are also called as core losses, or we can call them as iron losses. As we saw, the primary winding creates a flux in the core of the transformer, and that flux has an alternating nature. I told you phi is equal to phi m sin omega t. So, this flux is alternating in nature, due to which there will be two type of losses in the core. One will be hysteresis loss, other will be eddy current loss. These two type of loss occur in the core of the transformer due to the alternating flux set up by the primary winding of the transformer. So let us first consider the hysteresis loss. Now what happens is, all the magnetic materials that we used for the construction of transformer are ferromagnetic in nature. Now ferromagnetic material have a very special property that is called as spontaneous magnetization. Spontaneous magnetization means the magnetization that is present in the absence of magnetic field. That is, the magnetic dipoles in a ferromagnetic material are aligned even if there is no magnetic field present. Okay, they will be aligned, due to which they will have some magnetic flux density in the material even in the absence of magnetic field. So they have some residual magnetic flux density. This is the property of the ferromagnetic material. So since we are applying an alternating flux, okay, the dipoles will be oriented in one direction in the positive half cycle and in the opposite direction in the negative half cycle. So we have to supply some energy to the dipoles to orient them or to reverse their orientation. Okay. Here if you see, the magnetic field is 0, but due to remnant or the residual magnetic flux density, the dipoles will still be oriented in the same direction. So to reverse their orientation, we need to apply some energy, and this energy will be supplied from the source connected to the primary winding. Such energy or such loss is called as hysteresis loss. It only occurs because of the residual flux density in the core of the transformer. So the dipoles will get oriented in one direction and will not lose their orientation upon removal of the magnetic field. So we have to reverse their orientation, we have to rotate them by 180 degree. So that will require some energy, which is called as hysteresis loss. So ferromagnetic materials exhibit a hysteresis curve, something like this. Now this middle line, what does it represent? It represents a freshly prepared sample. That is, when a newly prepared ferromagnetic material is taken, it will not have any residual flux density. So it will follow the curve, which is the middle line. But when you demagnetize it, then it will follow a different curve. So again, now at H is equal to 0, this is B versus H. At H is equal to 0, the magnetic field is non-zero, or the magnetic flux density is non-zero. This is my residual flux density. And then again, if we increase, there is a different value of magnetic flux density. That is the property of the ferromagnetic material, and this curve is called as hysteresis curve. Okay, this is my hysteresis curve. It just denotes that while increasing the magnetic field and while decreasing the magnetic field, the path taken by the magnetic flux density is different. That is, for same value of magnetic field, magnetic flux density can have two different values depending upon whether you are increasing H or if you are decreasing H. Like if you see here, for the same magnetic flux density, magnetic field H, we have two different value of B. These two different values depend upon whether you are decreasing the H or you are increasing the H, on which curve you are traversing. Okay, the area of this curve indicates the hysteresis loss in one cycle. Okay, area is equal to hysteresis loss per cycle. Okay, so total loss is equal to area into frequency of operation of the transformer. Okay, this is the time period, so frequency will be 1 upon time period. So total hysteresis loss is given by area under the hysteresis loop multiplied by frequency of operation of the transformer. This frequency will depend on this frequency of the source applied at the primary winding. Whatever is the source frequency will be the same frequency of the operation of the transformer. Now how to estimate this hysteresis loss? This hysteresis loss is given by Steinmetz formula. Okay, it says that hysteresis loss is equal to eta. Eta is the hysteresis coefficient or Steinmetz coefficient, Bm raised to the power x into frequency into V. V is the volume of the core. So eta is called as Steinmetz constant, x is called as Steinmetz exponent, and this x depends on the type of material being used. Like x is equal to 1.6 for silicon steel or CRGO steel. X will be taken as 1.6. V here represent volume of core. So remember, hysteresis losses are directly proportional to the volume of core. If you change the dimension or the volume, then hysteresis loss will also change. And F is the frequency of operation. So hysteresis loss are directly proportional to the frequency of operation. Now, as we saw during the EMF equation that Bm is directly proportional to V by F. So hysteresis loss is equal to eta V by F raised to the power x into F into volume, which is eta V raised to the power x F raised to the power 1 minus x into volume. Okay, this will be the expression for the hysteresis loss. Now we can consider two cases if V by F is constant. If V by F is constant, I can consider this term as constant, then hysteresis loss is directly proportional to frequency. Okay, the higher the frequency, more will be the hysteresis loss. Next is if V by F is not constant, then hysteresis loss is proportional to voltage raised to the power x, frequency raised to the power 1 minus x. If you keep x is equal to 1.6, it will be voltage raised to the power 1.6, frequency raised to the power minus 0.6. This will be the expression of the hysteresis loss. Now if you keep voltage as constant, then hysteresis loss will be proportional to frequency raised to the power minus 0.6. Then on increasing the frequency, hysteresis loss will decrease. Now try to summarize this. If V by F is kept constant, then hysteresis loss is proportional to frequency. So by increasing the frequency, hysteresis loss will increase. But if you do not keep V by F as constant, but instead keep voltage as constant, then on increasing the frequency, hysteresis loss will decrease or hysteresis loss will reduce. So it depends how hysteresis loss varies with frequency. It depends if V by F is constant or if voltage is constant. That depends on that. Next, let us consider eddy current losses. Now, since we have an alternating flux set up in the core of the transformer, there will be some EMF induced in the core. If d phi by dt is non-zero, then EMF will be induced in the core. EMF of the core will not be equal to 0. Now due to this EMF being induced in the core, there will be some current induced in the core, which is called as eddy current. Why is it called as eddy current? Because as in a C, we have eddy flowing in a circular loop. Similarly, these eddy currents in the core of the transformer flow in the circular loops, hence these are called as eddy current. Eddy in a C flows in a circle. Similarly, eddy currents in a core flow in the circular loops. Okay, that is why when I was telling you about the laminations, I was telling you we laminate the core to reduce the size of the loop so that eddy current losses reduce. Now this eddy current will be directly proportional to conductivity of the core. The more the conductivity of the core, more will be the eddy current. And the resistance of the core will be inversely proportional to conductivity. Okay, resistance is rho L by A or L by sigma A. So resistance is inversely proportional to conductivity. Then eddy current losses, which are equal to IE square RE, will be directly proportional to sigma square into 1 by sigma, which is equal to sigma. So eddy current loss is directly proportional to the conductivity of the core. If the core is taken as a conducting material, then it will have more eddy current losses. That is why what we were doing is, we were adding silicon to the steel to increase the resistivity or to decrease the conductivity, so that eddy current losses will increase. But as I told you, silicon cannot be added beyond 4%, otherwise it will make the core of the transformer brittle, and we need to give the transformer core a shape for its operation. Now eddy current losses are given by some constant Ke into Bm square. Bm is the maximum value of magnetic flux density in the core, into frequency square into T square. T is the thickness of the lamination used to design the core. Okay. When we were laminating the core lamination will have some thickness T. That is why while doing lamination, I effectively reduce the thickness of the core. Earlier the core was this much thick, but after lamination the thickness is only reduced. So my eddy current losses will also reduce. Okay. So remember this dependency on thickness also. It is proportional to the thickness square. So thinner the laminations, less will be the eddy current loss. But if we make the laminations too thin, then it will be very much difficult to rivet the laminations together and keep the core together. Okay. So it may be possible that the core may disintegrate or the individual laminations may come apart if the laminations are too thin. So we cannot reduce the lamination thickness arbitrarily, otherwise the core strength will also reduce. So let us consider again the two same cases. First is V by F is constant, then Bm would also be constant because Bm is proportional to V by F. Then eddy current losses will be proportional to frequency square. Okay. But if voltage is constant, then eddy current loss is proportional to Bm square into F square. Now Bm square is proportional to V by F square into F square. So eddy current loss will be proportional to V square, which is constant. So eddy current loss is constant if voltage is kept constant and V by F is not constant. Okay. So eddy current loss will not vary with frequency if you keep the voltage applied as constant. So this is the dependency of the eddy current loss on the voltage and frequency. Now let us see how we can separate the eddy current loss and the hysteresis loss from the iron loss. See, we were obtaining iron loss from the open circuit test, but we were not knowing the individual components, that is the hysteresis loss and the eddy current loss. The only thing we knew was the iron loss. So what to do is conduct an experiment in which V by F is kept constant. We are varying the frequency and voltage such that their ratio remains constant. Voltage is not constant and neither is frequency, but their ratio is constant. Then we saw if V by F is constant, hysteresis loss is proportional to frequency and eddy current loss is proportional to frequency square. So we can say Wi is equal to Wh plus We is equal to Kh into F plus Ke into F square. Okay. So if you take Wi by F, then it will be Kh plus Ke into F. Now if you plot the graph between Wi by F versus frequency, it will be a straight line. Okay. The slope of the straight line would be Ke and the intercept would be Kh. So that is how we can determine Kh and Ke while plotting Wi by F versus F. And once we have Kh and Ke, we can determine hysteresis loss, which is equal to Kh into F, and eddy current loss, which is equal to Ke into F square. The only thing that we need is Kh and Ke. That can be obtained from the graph by the slope and the intercept. Okay. So this is about the iron losses and how we can separate them into its component. The next loss that we consider is called as stray load loss. So first of all, let us understand the meaning of the term stray load loss. Why is it called as stray? Because this occurs in the iron parts of the transformer which are not linked to the core or the winding. See, the transformer will have some iron structure. It is not only core plus winding, but it will have some outer shield, it will have a base, it will have a stand. All those things will be made of iron. So these losses occur in those iron parts of the transformer, hence they do not occur at a definite place. Like, I knew that the copper losses would be occurring in winding, I knew that the core loss will be occurring in the core, but these stray load losses do not have any fixed location. Hence these are called as stray. Next thing is that they depend on the load current, hence the term load. So these are the variable losses because these depend on the load current. But the core losses depended on the voltage and frequency and not on the load current, hence they can be considered as the constant loss. Copper loss also depends on the load current, so it is also a variable loss. So copper loss and the stray load loss are considered as variable loss because they depend on the load current. Now how does it depend on the load current? Due to the load current, let us say I2, a leakage flux is developed phi L2. This leakage flux will link the iron parts as well as secondary winding, due to which an EMF will be induced, due to which eddy current will also be induced, which will lead to losses. Okay, that is how stray load losses occur. The secondary current or the primary load current will generate some leakage flux. This leakage flux will link two things. One is the iron parts of the transformer, other is the winding conductor, and they will induce an EMF in those conductors or the iron parts, due to which there will be some losses which are called as stray load losses. Now, to reduce the losses in the conductor, what we do is we take the stranded conductor instead of the solid conductor. The cross-sectional area of the solid conductor is something like this. But in case of stranded conductor, this entire conductor is divided into small conductors so that we can reduce the eddy current losses. Consider this similar to the lamination of the core. To reduce the eddy current losses in the core, what we did, we laminated it into thin sheets. Similarly here, we divide our entire solid conductor into thinner conductors to reduce the eddy current losses. Okay. So even the stray load loss has two components. One is the losses that are occurring in the iron parts. That will be called as iron stray load loss. One is occurring in the conductors, that will be called as copper stray load loss. Practically these are 0.5% of the output power. Okay. So that is why stray load losses will be mostly neglected because they are very less in magnitude. But now I hope you understand their cause. The cause is the leakage flux which is developed due to the load current, and they occur in two locations. One is the iron parts of the transformer, other is the winding conductors. This can be reduced by making the winding conductor as the stranded conductors, but you cannot reduce the losses that are occurring in the iron parts of the transformer. The last type of loss is the dielectric loss. Dielectric loss occurs in insulators present in the transformer. Now insulators can be due to two reasons. One is the winding insulation. When I was telling you about interleaving of the winding, we were keeping an insulation between the core and the winding and between the high voltage and the low voltage winding. The other is due to the oil in the transformer. Oil also acts as an insulator, so it will also have some dielectric loss. Now what is the main reason behind the dielectric loss is that no insulator is perfect. None of the insulator can guarantee that there will be zero current through it. Always through an insulator, the resistivity is very high, the resistance is very high, but still there is a leakage current through the insulator. That leakage current may be in the order of milliampere or microampere. The current is very less, but still it has some magnitude. Due to this current, there will be some losses in the core of the transformer which are called as dielectric losses. Usually the core of the transformer is a magnetic material, it is not a conducting material. Still it will incur some losses which are called as dielectric losses. These dielectric losses are almost 0.25% of the output power. Okay, that is why they are neglected. Now these losses depend on the voltage applied instead of the current carried by the load. So these are also taken as constant losses. Remember the only difference between the constant and the variable loss. Constant losses are those which do not vary with the load current, and variable losses are those that depend on the load current. This is the only difference. It is not that constant losses cannot vary. They can vary by changing the applied voltage to the transformer. but variable losses depend on the load connected to the transformer or the current drawn by the load. That is the difference between variable and the constant losses. We will again encounter this dielectric loss when we will be considering the UG cables in case of power system. There we will derive the expression for the dielectric loss and it will be more clear. But for now, just understand these losses occur due to finite conductivity of the insulators. Otherwise, ideally the conductivity of the insulator should be 0. There should be no current through any insulation. But there is a current through the insulation, which is leakage current, and it is finite. So let us summarize what we saw. We saw 4 types of losses. First one was copper loss, which we wrote as I1 square into R01 or I2 square into R02. Then we saw core loss, which had hysteresis loss, which was eta Bm raised to the power x frequency into V. X was 1.6 for silicon steel. Then we saw eddy current loss, which was Ke Bm square F square into T square. T is the thickness of lamination. And then we saw stray load loss, which occurs in the iron parts and the conductors of the winding. And last we saw dielectric loss, which occurs in the insulation, that is the winding insulation or oil present in the transformer. In the next lecture, we will see how to determine the performance of the transformer, how to determine which transformer is better and which is worse. That we will see in the next lecture.